Well, hi everybody, I'm Michael Tucker, and today I'm going to be talking about how we can improve computer simulations of nuclear reactors. So just a little bit about me and my research group. I'm a PhD candidate in the Department of Engineering Physics, where I work under the supervision of Dr. David Novell. And our research group is focused on industry-driven safety analysis in both the reactor physics and the reactor thermohydraulics fields. My research specifically looks at how we can better understand uncertainties in computer simulations of nuclear reactors, and perhaps more importantly, how we can minimize the impact of those uncertainties. So just a little bit of background on nuclear power in Ontario and CANDU reactors. The Canada Deuterium Uranium Reactor is a Canadian nuclear reactor that was first created in the 1950s. There are 18 operating CANDU reactors spread across 3 nuclear power plants in Ontario, and collectively they produce 60% of the province's power. There's also 1 CANDU reactor in New Brunswick and a number of CANDU reactors spread across the world. And together these plants have a long history of safe, reliable operation. And importantly for Ontario, the ongoing plant refurbishments mean that CANDU reactors will be part of Ontario's electricity production for at least the next 40 years. Now, computer simulations are a very important tool in the safety analysis of a nuclear reactor because they allow us to predict how a reactor will behave in a situation it's never been in before. This is particularly important because we can't do experiments to see what will happen in the unlikely event of an accident. But of course, nuclear reactors are quite complicated. I don't think that's a surprise to anybody. And so properly simulating a reactor requires a number of steps. One of the main challenges is that computational power is finite, so we have to find ways to simplify the model so that we can simulate it with the available resources. One of the ways that we can do that is by breaking the process into a series of steps. And what that does is it allows each individual step to be more detailed than it could be if we had to do all of this as one single simulation. So I've got an example of some of the steps here on the slide. One of the first steps is to collect and analyze experimental data on how neutrons interact with the various materials that we would find in a reactor. The next step is to take all of that experimental data and simplify it as much as we possibly can and convert it to a format that a computer can understand. We then start by simulating a single cell or building block of the reactor, typically on the scale of 1 sort of fuel assembly. And we look at that fuel assembly under a number of different conditions. Different temperatures, different coolant densities, different fuel ages. We may simulate the presence of a control rod in the vicinity. So we basically are creating a database that shows how the fuel will respond over a wide range of possible situations that it would encounter in the reactor. And then by combining many of these building blocks, sometimes in a repetitive lattice sort of shape, we can build an approximate model of an entire reactor core. And we can take that approximate model of the reactor core, which gives us a fairly accurate idea of how the reactor responds, and we can combine it with a similar model of the thermohydraulic properties of the core, which basically looks at how fluid moves and how heat moves inside the reactor. And by passing information between that core calculation and that thermohydraulic calculation, we can come to a converged solution that predicts how the reactor will respond in this new scenario or transient. Now, like I said, my research is all about the uncertainties that we find in these simulations. And so a few of the possible sources are shown here. The first would be input uncertainties. That's when the researcher, me in this case, doesn't know the exact value for the various parameters that we have in the model. For example, we may have experimental uncertainties in our neutron material interaction probabilities, or we may not know the exact geometry of the fuel because of things like manufacturing tolerances. We have modeling uncertainties, which arise from the simplifications to the complex physics that we have to make in order to actually be able to simulate these with computers. An example of that would be if our initial or boundary conditions in the simulation aren't perfect. We have numerical uncertainties. Those arise from the techniques that computers use to solve the complex equations that are at work here. And we have what we refer to as the propagated uncertainty. And this arises because of the linear path or the linear technique that we're using to do these simulations. Because the output of each step of the process is an input to the next step, any uncertainties on that output become an input uncertainty to the next step. And so what that all leads to is a non-linear and complex path for these uncertainties to combine. It's not always easy to predict how these uncertainties will combine and create an uncertainty on our final key outputs for the safety simulation. We also have to remember that a small uncertainty on one parameter may be more important than a large uncertainty on another parameter, or that some uncertainties may cancel each other out while others may amplify each other. So I've taken the block diagram from before, and I've just shown a subset of some of the possible sources of uncertainty and the way that they can move through the system. So like I said, we have uncertainties that may arise from our experimental data collection or from the expert judgment that we use to analyze that data. We also have uncertainties that may arise from the modeling choices we make, like the format of the nuclear data or the format that we're putting that data in so that the computer can understand it. We may have uncertainties that arise from our imperfect knowledge of the reactor. We may have uncertainties that arise from, for example, our simplified approach of modeling the reactor as a series of building blocks stacked on top of each other. Finally, we may have some uncertainties that arise from our imperfect knowledge of conditions, or we may have some uncertainties that we just can't possibly know, like if the condition of the pipes have started to degrade over time. Now, I've just thrown a lot of information in all the different ways that these uncertainties may make these simulations and their outputs not quite known. So I want to stress something really important, and that's that these simulations are safe. Despite the overwhelming number of sources of uncertainty, there's been an acceptable approach in use in the nuclear industry for a number of years, and that's what we call the conservative approach. And so in the conservative approach, to ensure that the impact of uncertainties doesn't take the plant from a safe state to an unsafe state, we run a simulation where we assume that all of the inputs are at their worst possible values. Now, what that gives us is a sort of bounding accident or a worst case scenario. And we can, by looking at that worst case scenario and ensuring that it's within our operating envelope, we can infer that our simulation results are acceptable. Now, there's a number of drawbacks to this approach. The first is that the worst case scenario is very good for understanding sort of what, again, the worst case is, but it doesn't give us a good idea of how the accident evolves from safe operating conditions to that end state. So a better understanding of the early stages of the accident is actually very important because it can allow us to detect it and then correct it sooner, which may actually result in the accident being avoided altogether. Sometimes the assumptions that we have to make in this method don't necessarily make sense. And the conservative approach means that our safety margins are often larger than necessary. And that actually drives up the cost of electricity, especially when more than half of Ontario's power comes from nuclear reactors. So an increasing area of international interest is the best estimate plus uncertainty approach. It's sort of a replacement for this conservative approach. And in BEPU, the most realistic set of inputs for a simulation is identified and used. And that gives us what we call our best estimate. Then, for each of the simulation inputs, we look at them and we derive some sort of uncertainty. How certain are we that this is the correct value? We can then perform many additional simulations where each parameter is randomly sampled based on what we think it is and what we think the uncertainty is on that. The result gives us a clear picture of how the event is expected to unfold. That comes from our best estimate. And it gives us an envelope of all the other possible and reasonable responses. So the advantage of this is that it maintains the safety of the conservative approach, but it significantly reduces those drawbacks I was talking about. So for CANDO reactors, what we've done so far has looked at how we can account for some special operational feedbacks that aren't present in other reactor designs. These feedbacks can significantly reduce the impact of some of the other uncertainties that we look at. And I have an example of that here on the slide. So the neutron multiplication factor is often looked at when we're doing these safety studies. And on the left of the slide, or I suppose the right when you're looking at it, we can see, no, it's the left, we can see the distribution of the neutron multiplication factor before we account for those special operational feedbacks. On the right, we can see that once we account for those operational feedbacks, the distribution becomes much narrower. And what that means is that our uncertainty in that parameter is much smaller when we account for these things. So the work that we're currently doing is looking at, over the next 12 months or so, performing a best estimate plus uncertainty study on a CANDO transient that has previously been studied using the conservative approach. So that will give us a good way to compare the impacts of BEPU versus the conservative approach. I'm only looking at a subset of the uncertainties, but we've selected them because we believe they are the most important. And so our future work will expand not only the types of uncertainties that we're considering, but also the range of transients or scenarios that we're covering. There is another slide. All right, so the conclusions. The best estimate plus uncertainty approach offers a number of advantages compared to the typical conservative approach, but it does require a thorough analysis of the sources of uncertainty to that reactor simulation, And specifically in the CANDO reactor case, it requires that we analyze these special operational feedbacks. Now, our current work has been very promising, and we're hoping that the BEPU analysis will eventually lead to a reduction in the average Ontario resident's electricity bill. Thank you very much.